So, good morning. It's an interesting start, right? And it's great to talk about errors, like we just encountered errors, right? Okay, so this keynote is really about an interesting idea. It's about the idea that essentially errors are something we can basically use. The potential for errors is a thing that we can use in the context of design in order to go and figure out what we need to do from a design point of view. Quite often when we're in software development, what we try to do is we try to go and get the happy path first. We try to go and say, oh, let's go ahead and get like the minimum viable product. Let's go and do the things it takes to go and sort of get the core business value. And quite often that isn't dealing with the error cases that happen at all in the system. And that's okay. But the thing is, I think there's value in actually going and saying, hey, let's look at the potential for errors. And when we see that potential, let's go ahead and do something about it. And quite often we can end up with designs which are a little bit more robust and actually a bit simpler too, in some cases. So I want to go and sort of like ask a question at the very beginning of this though. What are errors? Okay, does anybody have an idea of what an error is? We all just kind of know what errors are, right? Yeah, it's like it's a bad thing that we don't want to have happen in the context of our software, in the context of our systems. But I want to kind of reframe this in a sense. I want to basically say that, look, maybe errors are just conditions that we refuse to take seriously in design, okay? Now, this isn't going to make much sense in the very beginning, but as we work through some examples, hopefully you get a sense of what I'm going on with here, okay? So here's like a parking application, okay, like a parking app for the iPhone. Think about all the things that can go wrong when you're trying to select a parking spot, right? One of the nice things here is they essentially gave us a list of the recent spots we've been in, and you can kind of like select one of those particular sections. Or you can go and type in another number, right? What happens if I type in too few digits? Probably going to get an error message, right? What happens if I type in too many digits? Probably get an error message also. Or it could just constrain the field to go and say, look, you can have no more than 5 digits within it, right? There's all these things that we have as like back and forth with the user, okay? Things that we sort of like try to go and have in place to go and basically make the accommodation of the user's intent nicer, okay? We often end up in situations, though, in software where we actually have to go and sort of like say, no, I'm sorry, I can't deal with the input that you've given us. So, for example, people using Amazon, right? There are numerous different error messages that can come up in the context of going and buying things, right? We have a couple over here. Essentially, okay, here's something going and saying you have to accept third-party cookies. Your session is expired. Some of these things are related to, session state within the context of an application, a web application. But this is never nice to go and give to a user, right? You like to be able to work with a user's intent in order to go and actually get things done. And the thing of going back and saying to people, oh, the thing that you want to do, you can't do right now, is something we should feel kind of bad about in software development. So let's look at something else. We look at something which is far simpler than a web application. Does anybody know what this stuff is that we have at the top here, this notation? Okay, for people who play guitar or work with some other stringed musical instrument, you're probably familiar with this. This is called tablature. And tablature is a way of going and notating music that's kind of very specific to stringed instruments. What it is that essentially you have 6 different strings on a guitar, and the top one here basically it tells you the positions you place your fingers, your left hand, when you're going and playing a tune, for instance. And let's imagine that we're going to try to go and create this notation using some kind of input. And our input looks kind of like this, okay? So you might not see the mapping immediately, but what's going on is that here's a file of numbers, pairs of numbers, and the very first number is going to be the string number. We're numbering the strings from 1 to 6 downward, those different lines we have in the notation. And the right-hand number, the second number on each line, is actually the fret position, the position where you actually will place your finger. So I guess we can kind of see there is a bit of a mapping between these two things. Essentially, the first line here goes and says that for the first string, we will be pressing the 0th fret, or we'll be playing the open string. And you can kind of like move further down there and see that every one of these lines corresponds to a column going forward in the context of our stuff. So it seems like a very simple program, right? Very easy to deal with. What if somebody goes and does this? What if they give us less than 2 numbers per line? Could happen, right? So what do? We go and we print an error message and say, oh no, it's terrible, you basically gave us 1 less number than we expect. We reject your input. Is that a nice thing to do to users? not so nice. But here's the trick, and this is a trick that I hope you carry forward, and this is a trick that works in all different kinds of applications at all different levels. What if we consider this to be good input? Can we change our problem so that this is good input? Well, one thing we could do is we could say that when we have only one number on a line, the second number is an implicit 0. And so we can essentially see this as being good input. Is this a good way of handling this? We can go back and forth about this. And I'm going to talk more about this a little bit later. But essentially, sometimes we can actually go and accept wider ranges of input as long as we can give them meaning, and then basically have one less error to deal with in the context of our interaction with our users. So we'll let that sit for a little while, and we're going to go on to some other things and talk about it. So yeah, we have that possibility to go and actually sort of massage our input that way. And if you look here, this is kind of like a list of all the things I could imagine could go wrong with this program, right, in terms of things we might have to go and check for. It's a program that works at the console, okay, like written in Ruby. And you can see here that maybe, our command line argument happens to be a file that we input, okay, about those pairs of numbers. Maybe the file name is missing. Maybe we can't open it. Maybe it's not a text file. Maybe the file is empty. Maybe the file contains some empty lines. So there's all these different things that can go wrong with this, but we've just been able to go and sort of like eliminate this one particular one. Okay, if a line has less than 2 numbers, now we're going and saying that that's acceptable input because we've given it a meaning. Can you imagine fixing these other things so they can't happen in our program, or if they do happen, it actually has a meaning? Some of them yes, some of them no. So, for instance, take number 3. The file contains empty lines. Maybe we just go and say if we have an empty line, it just doesn't matter. You can have an arbitrary amount of space between sections of numbers, and that's an acceptable format, right? So we can be a little bit less strict about what our input happens to be. What if our file is empty? If our file is empty, maybe we have no output, and that can be okay also. So we have this scale in terms of going and checking for errors in systems that we can pay attention to all the time and try to figure out how can we actually go ahead and accept more programs that are going to be aligned with the user's intent. So there are some other ones here that are interesting, and we'll talk about them a bit more later. Look at 8 and 9, okay? The string number is a number between 1 and 6 because we have those 6 lines representing each string in our program. What happens if we put down a 7? Is that an error? Something to think about. What if the fret number is, greater than, say, 24 or 25 or something like this? Should that be an error? I don't have an answer, but these are things that we can go and discuss. The interesting thing with all this is that essentially for most programs, and even very small pieces of programs, you can use this interesting mental frame for them and go ahead and say, look, it's great when we can actually go ahead and deal with all the problems that can occur at the edge of some domain. And then once you get inside that domain, then you don't have to deal with any errors at all. So it's kind of like creating these protected spaces in the context of our program. And the cool thing is that essentially if we can go ahead and sort of like eliminate the possibility of these things being problems at the edge of our program, then the code that we have inside can become much, much nicer. It can become kind of like there's very little checking that goes on. There's no possibility of error because we've sort of like protected the main path. And that's a nice thing to be able to do in the context of most programs. So it's nice to be able to go and push checks to the edge whenever you can in the system. Okay, so here's some interesting code. Okay, is this good code? Of course it's good code. It's C#. And everybody knows that's, no, okay. Yeah, I'm not going to be a zealot about that because I don't really believe that, right? But the one thing I find very fascinating about this is just the whole thing of checking for null. We're checking for null all over the place here. Why are we checking for null in this code? Well, because it could be null, right? And it's like if you look back historically at most code that ends up looking like this, what you discover is that every one of these checks is there because somebody had like a null reference exception or a null pointer exception that came out in the system, and somebody says fix it, and then how do you fix it? You put a check to basically make sure it can't happen. But this is really kind of horrible because essentially, for our code to get in this state, somebody had to have passed null to us. So if you look at, say, one of these things, for instance, it's like we have a message completed. We check to see whether it's equal to null or not in one place. That's an argument that comes into this function. If nobody passed null, we wouldn't have to check for it, right? Now, I know that null is a essentially a thing people have been dealing with for quite a while in the context of language design, in the past 10 years or so. You have languages like Rust, you have F#, you have various different languages which try to go and do this thing of going and trying to basically manage null within the context of programming. That's pretty powerful. But I think that null is actually symptomatic of something bigger. But we all recognize it's a problem. So you all know who Tony Hoare is? Okay. So he basically said this. Essentially, he feels that this is the biggest mistake he made in the industry, was introducing null into language design way back in 1965. On balance, this is also the guy who invented quicksort, so I think that he it kind of balances out for him, which is good, right? But yeah, null is a problem, but it's really a problem that's based on something which is a bit bigger and symptomatic. Let's go ahead and take a look at some stuff here, right? Here's a little piece of code. Okay, we're asking for an item for a barcode. We pass in the barcode as a string, and we attempt to go and get it from a collection, and if what we have is null, it's not null, we return the item, otherwise we return null, right? We're being very explicit about this, but here's the thing, we can return null back from our query. Is that good? Well, it's rough because anybody receiving a reference from us has to check to see whether it's null or not. What happens if they don't check? If they don't check, we get an NPE, we get some kind of a problem, all right? So what's an alternative? We could do something like this, right? We can just throw an exception. Is that better? Yeah, and this is one of the things I kind of hate is that so much of the conversation we have around errors in the context of programming comes down to which mechanism are you going to use. When I think the bigger thing to go and ask really is like, okay, something bad has the potential of happening in your program. What do you want to have happen? And if you concentrate on that, then the mechanism doesn't matter quite as much. So let's look at this a bit further. Exceptions. This guy, Bertrand Meyer, back in the 1980s, he basically was giving advice about exceptions, and he said, essentially, use exceptions when you can't know in advance whether a call will succeed or fail. When is this true in the context of programming? You can't tell in advance whether a call will succeed or fail. Usually it's when you're at the edge of a system, right? When you're dealing with I/O, okay, or you're going and talking to third-party libraries where you have the potential of not getting the thing that you care about. In those cases, things, exceptions can be kind of like a nice thing to be able to do. The powerful thing about exceptions is that essentially they can put some distance between the detection of a problem and how you choose to respond to it. That's the good thing about exceptions. You know what the terrible thing about exceptions is? It allows you to put distance between the detection of a problem and what you do about it, right? That distance can be good or bad in the context of systems. So let's look at this here. We can essentially go ahead and throw an exception. And that's okay, but this kind of forces people someplace another part in our system to deal with that exception and do something in response to it. That distance can be okay, it can also be a problem. Quite often it is a problem for us. It's nice to be able to go and sort of like ask the question, what is really going on here? What is the thing that we care about? And be able to do something about it. So I call this tunneling, okay? Essentially when you have something happen over here and it forces you to do some work to go and decode things over here. And it's kind of a thing which it's nice when you don't have as much of this thing, tunneling in systems. Let's go and look at this a bit deeper. Okay, here's, essentially like we have this particular function, populate signs, and somebody goes and calls it with null, right? That goes and causes some trouble for us because somebody passes a null in. What are we obligated to do inside of the function? We're obligated to check for null. So we have this thing where we're kind of like passing something in, we're forcing checking in some other place in our program. And it's really, when you look at it, it's kind of like extra work that you have to do, right? So why do we have to do this extra work? Do you see that this is kind of like forcing something on the user of our code? Okay? So essentially, we're passing a null inside there using the parameters. We are forced to do something. Isn't this analogous to what we had in the user interface also? I'm working in the user interface, and I'm forcing them to deal with something I can't handle. So I go and I say to them, error, and they have to go and do something in response to it. So that kind of thing of forcing work on people is a thing that's great for us to be able to eliminate in context of systems. So I think null is kind of problematic because it quite often forces users to pay the price for things that we don't know. And if we can work around that to some degree, then things are a bit better. Okay? And essentially, error handling is the structure we put in between failures and the solutions that we have for our things. Let's take a look at another example of this tunneling thing I was talking about. So I'm wondering for you developers in the room if you've run into this situation where you have a method that has maybe 100, 200 lines in it, right? And one of the things that happens is that all through the method, you're going and setting Boolean variables about particular things that you found. And then way down at the bottom, you have a bunch of different statements where you say, if I have this and I have that, then I can do this. If I have this and I have that, but I don't have that, I do this, right? Ever see code like this? Isn't this the same thing? You're kind of like creating a bunch of things that you have to interpret later in the context of your code in order to go and basically do your work. So this tunneling thing can lead to some pretty horrendous code sometimes, and that can be problematic for us. Okay? This also happens in the context of like working with strings. Sometimes in some languages, in some programs, you have people encoding information in strings only to decode it later. You create little formats, you decode them later. And that can be problematic. And now, we have things like JSON and stuff like that. That's a very good language in the sense that we have decent parsers. But we also introduce the possibility for error if we have like ad hoc languages we put in strings and if we have to decode later in the context of our code. It's tunneling, and it can be problematic. So can we eliminate tunnels? Let's go and look at a possibility here. Okay, so here's our throwing an exception when we can't find something. Something else we could do is we can do something like this. Okay? I'm going to go to my collection and ask for a particular item associated with the barcode. And if I can't find that particular item, what I'm going to do is I'm going to create a new item. And its name is going to be item not found. And the price of this item is going to be 0. Is that okay? Can be. It depends upon the domain. Does anybody know what the name of this pattern is? There's a name for this pattern. It's called the null object pattern. And essentially what it is when you say, look, and rather than going and having an error, what I'm going to do is I'm going to create an object which represents the absence of an object. And as long as that object can play well within my system, everything's going to be okay. Now, if you're in a system where you're going and getting items and you're probably like totaling them up, having an item with a price of 0 is actually okay. You can kind of total up all the items and this one isn't going to hurt anything. If you have logic that depends upon the number of items you found, this is a problem because essentially this is an item that represents the absence of an item. So this can either work or not work, but this is a thing that you can do. And you'll notice that with this, there's no real tunneling going on. Essentially, you have the possibility of an error, but you're creating something which is going to be a stand-in such that you don't have to do any checking later. So this is a thing you can basically do to approach these kinds of problems. So there are many different examples of this kind of thing in programming. Sometimes people will use an empty list to go and represent the absence of something. I ask for all the items with a particular ID, I get back an empty list. You can map over an empty list and everything is okay, right? So you don't have to deal with the error explicitly when things like that happen. Not a number in floating point arithmetic also represents the absence of a solution to a particular mathematical operation. So these are ways of kind of like going and saying, look, here are some things I can actually have within the context of my code to make sure that I can still continue processing even though an error has occurred. Okay? There's another interesting thing that we can do with some of these things too. There's a guy named Alex Sharp, and he basically said this many years ago. He said, procedural code gets information that makes decisions. Object-oriented code tells objects to do things. Have you ever heard this saying in programming? It's like, tell, don't ask. Have you heard about this at all? Some of you have, some of you haven't. And really it's kind of like a guideline for good object-oriented design, that in general it's better to go and do some processing and tell another object what your result is. And then it receives that stuff, and then it goes and tells others to do things. That's a better style for object orientation than going and saying, I'm going to get something from you, get something from you, get something from you, compute using those things, and then do something with it. Because it tends to lead towards a better dependency situation. It also tends to be better for error handling in a way too. So how many people are doing any kind of functional programming right now? Yeah, more and more, because a lot of languages are getting very functional features these days. But an interesting thing is that when you do this thing of saying, I go to something to go and get an item, if the item's not there, then what do? You return null. That's the thing which is possible with this because you may not have an item. What happens if you just instead say, look, I'm going to go and get an item, and I'm going to tell somebody about the item that I have. And if I don't have that item, I just don't tell them. That's better from an error handling perspective also, isn't it? Okay? In that context, it's like something is missing, and you just don't tell the receiver about anything at all because there is no item for this. You may tell somebody else that there was an error, and that's a good thing also. But the style of going and telling people when you have things is often better than going and saying, let me go ahead and return things back to people that I have gotten or not been able to get. So this can eliminate some of the error handling code that we might have in systems. And it's interesting because we can apply that sort of thing all over the place in systems. If I have something in the sale domain, I might go and tell people about the things that can happen in a particular transaction. I can say, we'll have an item was added. I tell somebody that an item was added to our system. I tell somebody that the sale was totaled. We can also extend this out and say, look, we were unable to find an item. So this is the barcode for the item that we were unable to find. Now this is interesting because this is going and actually dealing with an error case, but we're not using exceptions. We're not using null returns or anything along those lines. What we're doing is we're basically taking the particular problem that we have and we're making it part of our domain. And that's kind of powerful for us. Quite often, as I was saying earlier, we can avoid some error handling mechanisms if we choose to actually make errors part of our domain. And this is valid because there's not a system that does sales in the world that doesn't have the possibility of having something that's not in inventory. So we have this as an option. And again, this is part of that tell, don't ask style, which is kind of useful at times. So this is really an example of extending the domain to go and actually cover the things which are cases which are problematic, things which we might normally see as errors. And it's an ideal strategy for many systems. Extending the domain is something which we can do in many different areas. And I'm going to use a very liberal definition of domain. It's like domain is like, the domain of our business, right? There's also the sense of domain in mathematics, right? Where you have the domain and the range of a function, okay? Let's look at an example here. Suppose I have like a list of ones and zeros. I'm using shading to indicate the ones and no shading to indicate the zeros. Suppose I want to count up the number of spans of ones. How many spans of ones do we have here? 3, right? We start with 1, then we have 1 in the middle, and we have 1 at the end. Suppose I wanted to write code to actually count the spans of what do we have here. Well, I can do this in Ruby, and it ends up looking like that. Is that code to be proud of? Yeah, no, it's complicated, and it has to do with something really kind of odd. It's like we can count the spans by going and saying, okay, if I'm at a 0 and the next one's a 1, that's the start of a span, and that's a good heuristic, except for the very first case, because essentially you're either going to start at a 1 or you're going to start at a 0, and you have to know which. So here we're going and checking to see whether the first one is a 0 or a 1, bumping our count based upon that, and then going and looking at every successive pair in order to go and count up the ones that we have remaining. To me, this is ugly code, right? It has too many edges, too many discontinuities to it. But there are easier ways of doing this, and one is to go and actually say, look, we can get rid of some of those discontinuities by going and just hypothesizing an element at the very beginning, okay, and imagining that it's a 0. Once we have this, then it's easy for us to go and kind of like iterate through the entire thing and say, I'm starting at the very beginning. If I see a transition from 0 to 1, I bump up the count. And whenever I bump up the count, at the end I'm going to have a count of all the spans that I happen to have. So I'm extending the domain by going and adding a 0 to the very beginning of it. Can you see that there's a relationship between extending the domain this way and also like extending the domain this way? It's kind of interesting. It's like domain in a very broad sense. We have the domain of our business. Here we have the domain of our input, okay? What is our input? And we're going and expanding things this way. The code for this becomes much simpler, okay? And this is like written in Ruby. What I'm doing is I'm taking an array and I'm prepending a 0 to it, and then I'm going and using this each cons method, which gives me each successive pair, and performing a count whenever we have a transition from 0 to not 0. I won't elaborate further on this, but I'd way rather go and maintain code like this than the code I showed you earlier, right? So we have that. Extending the domain in other ways. Have you ever worked in a language like this where you can index using negative subscripts on arrays? This happens in some languages, right? Is that error prone? Well, there's a lot of languages that do this now, and actually once you understand that this is a thing that you can do, then, what's the worst case of this happening in a way which is a way you don't expect? Could be you have an index which ends up going and doing a lot of arithmetic and it overflows to a negative number that just happens to be inside of your array range. And the chances of that happening are very, very low. So actually this is relatively safe to go and say we're going to basically use negative subscripts in order to go and index into arrays from the right, okay? You can do this. But I'm wondering who actually did this first, what programming language actually did this first, because there's this thing of like when people don't know this is how you work, it's confusing. You look at this and you're saying, why am I having a negative number for an array? But somebody made that decision, and once that becomes part of the way that we understand the problem, then it gives us, it expands the range of things that we can accept as input. We have fewer things to go and check for. This is very much like what I was showing in that example with the guitar notation, where we say pairs of numbers, and if we don't have the second one, we just default it to 0. So we're being very clever about our domain here in order to go and basically accommodate increased functionality as well as decrease some checking that we have to do. But I think there's a rule about this, and essentially the rule is, okay, something about what we had with this projector thing. It's good to extend the domain only when people can see that extended domain as being the real domain eventually. Okay, I want to talk about another thing here too. So remember how I was talking about tunneling earlier between the point of detection of an error and what you're going to do about it, right? There's a concept I've been using quite a bit in programming recently. I call it an intention, okay? And it's really this notion of saying, for anything you're going to do at any scale in a system, is to basically sort of like satisfy some intention that the user has or the system has at a low level. And it's very much like when you throw exceptions, it's kind of like, you can almost see exceptions as being like transactions in a way, right? It's like we say that this should proceed, and if it doesn't proceed, we should at least get back to a good known state if it doesn't work. But you can see intentions at all different levels of systems. So let's kind of like make this a little bit more real. Everybody has some kind of like a music shuffler in some way, right? So if you're using iTunes or some other device, you have a playlist, you're able to go and sort of like say, shuffle all these tunes, and let me go and hear them in whatever, random order that the system determines. Imagine we're writing code to go and do something like this. If we are, okay, this is like 0 to n minus 1, the elements inside of our shuffle. Okay, so we have current rand n, we have rand. So we're going and getting a random number that happens to be bounded between 0 and n minus 1, and we're going to pick that particular tune and play it. Sounds like a good idea? Very simple code. What happens if the same tune is played twice? Users probably won't like that sort of thing. So what can you do? Well, a very naive way of handling that is to go and do this. Essentially what we're going to do is we're going to go and get the current random number. We're going to check to see if it's the same as the last random number. And if it is, then we'll go through a loop again and go and actually, check and see, is everything okay? Is this okay? Yeah. In the case of a list of 1, it's going to just play that forever. Well, maybe that's okay, right? But even beyond that, this is the kind of code that as a software developer, you should basically it should make you cringe inside because you're like, we have an infinite loop there. What happens if we keep getting the same number over and over again? And with any decent random number generator, that's not going to happen, but someday it could happen, right? You don't like to go and have that incongruity there, the fact that something may not happen all that often in practice, if ever, and the fact that it's possible, right? So you can do additional work to this and say, well, let's make things a little bit more complicated. Let's go and say if it's equal to the last one, what we'll do is we'll basically go ahead and sort of like, we'll take the next one modulo the list size. So we're always kind of making an advance to the list. So this code is a little bit more complicated, right? Yeah, a bit more complicated. You have to look at it and understand what the intention is behind it and all these other things. Well, what if you look at this and say, this code is a bit too edgy. It has too many decision points. What can we do to make it simpler? Well, one thing you could do is say, well, gee, what if we sort of like negotiate with the people who want the software and say, look, here's another feature you can have. And instead of just having like a straight shuffle of the list, we can also go and do things in a way where we guarantee that you're going to go and run through the entire list before going and playing anything over again. Users might like that sort of thing. And if that's something they might like, what you do is you say, here's a different solution. Let's just go ahead and start out with our list. We shuffle it in place, and we start going and taking elements from it. As we take them, we go and delete it from the list. So we've made a copy of the list, and we delete the ones that we've seen already. Our logic for this is going to be much simpler than what we were just looking at, okay? We essentially make a copy, shuffle it, and basically sort of like take the first one, and then take it off the list, and move on through the list like that. Much simpler logic than what we had previously. So here's the thing. Sometimes you can have a win in your coding when you actually revisit requirements. And it's important for us to be able to do this because, we can accept requirements as given in design, and that's okay. But code that can basically satisfy user intent, but also go ahead and make our code cleaner is a nice win for everybody, because whatever complexity we introduce in our code is stuff we're going to have to live with for many, many years. So it's nice to keep things simple as much as possible. So there is this thing about intention in programming, which I think is kind of powerful. And that is that whenever you have some place in your code, even deep down in the system, the potential for an error, just ask yourself, okay, what's the intention here? What am I trying to do? And it's like, why am I trying to open a file, for instance? And it might be, I'm trying to open a file because I need to go and load the configuration for my server. So you can say, well, if I can't open the file, how do I satisfy the intention of having the configuration anyway? And maybe you can basically load a default configuration and then notify the user that the default is there. That may be a potential solution. It may not be a potential solution. But you should be thinking all the time of, if there's a potential error here, how do I satisfy the user intent? And when you do, then you can make things better quite often and decrease the amount of error handling code you have in the system as well. Have you ever heard this advice before? Fail fast? Yeah, so I think this is fine in some systems. And quite often it's irritating to me because sometimes I encounter people who say, this is what you should do all the time in systems. Always fail fast. And it's like, it's great, but it's also like, it's a little bit lazy, and you can take time to elaborate cases over time. Maybe it's a good way of kind of bootstrapping a system. But I think that you can end up producing very brittle systems this way, okay? And I think that's kind of problematic. So there is an alternative school of thought, though, within software development. And that's essentially that, why don't we just go and consider failure to be normal and work with it, okay? And this has to be something we deal with all the time in distributed systems. It's like people who basically have like cable television or something like this. In the old days, you would have a remote control you would use like this. Now, many people can use apps on their phone, and you can be sitting as a family in the living room, each going and playing dueling remotes on their phones to do these things. But it used to be that all the software for selecting channels on streaming stuff like this used to be in a set-top box where the code was embedded in firmware. Now you have many devices able to play, and all these things can essentially, they talk to remote servers, okay? And you have network communication every place in the system. So most of the code can live on a server someplace. And this is analogous to most everything that we do these days. Quite often we are dealing with servers as opposed to having things locally. And the thing about this is it introduces many, many more error cases, many more possible error cases in our systems. Okay? And there are systems where basically, the price of errors is pretty high, right? So if you have a satellite that's way off on the edges of the solar system, you better make sure that software is right because it can't really be updated easily. Actually, for some of the probes that we have far out in the solar system, you can update that software. It just takes forever to do it. It's like a long send of a signal across the solar system and takes days maybe, But, there are more localized things, like elevators. Elevator controllers, do you want to go and have that talking to a server someplace to make decisions about how to open the door or not? You better have some plan B, right, in case your network goes down. So there's this thing that essentially when we have no human around to go and tend the system, we have to basically make sure certain things are right, okay? And that's really pretty important. So you need a human in the loop in those kinds of systems. And this is also a problem too. For some programs, the biggest error is stopping ever. There's also the thing of like, say, like medical devices. Like you might have like something for like diabetes or like a pacemaker or something like this. That stuff has to work all the time, right? But there is this other tack we can take for handling errors, which is to go and say that failure is possible. So let's make sure that we can behave well in the context of failure. So you've heard of Erlang at all? The Erlang programming language? Okay, if you haven't heard of this language, I encourage you to read about it. The same ideas are present in the language Elixir, okay, which is kind of like a rubification of Erlang in terms of syntax. But the idea behind this language is that essentially, whenever you have more than one machine talking, you have failures that are possible. You just have to deal with it. And so what it does is it tries to go and normalize failure and basically allow systems to operate in the presence of failure. Okay, so the way it handles these things is to go and say, look, for your system is composed of processes, and processes are not like operating system processes. They're kind of like very lightweight little things that sit as processors. You send them messages asynchronously, They do their work, they send messages to other processes and things like this. But some of these processes can be on a different machine, and what if that machine goes down? Your system should be able to behave well regardless. So the way it handles this is by having certain protocols in place so that if you have particular processes and they can't be communicated with, the system will notice and then destroy those processes and then recreate them, or allows you the potential to recreate them. And the way it handles this is through something called a supervision tree. So here's a system where you have like the root of all processes. And what you do is you basically say, we have a process for tallying things, for instance. This is a system for recording like votes in an election. And so you can basically go and get votes from the district, and you have districts like Quebec and Ontario, and you have counting processes, and some things at low level may touch hardware and have transient failures. If those things have failures, they get destroyed, and then the district will go and actually recreate those pieces. If the entire district thing can't work, the tally will go ahead and recreate the district. And so you have this dynamic thing where basically failures don't cause the system to go down because the system is organized to basically consider failure to be normal and say that there will be strategies that we will use when these particular things fail to be able to go and create new things. Now, you may not have heard of Erlang, but the thing is, Erlang is all around you. I was reading something the other day saying that 90% of all network traffic goes through Erlang-based systems, okay? There's a language that was made at a company called Ericsson in Sweden many years ago, in the 1990s, I think. It was very far ahead of its time. But it was basically built for this particular domain of having telecom switches that must run all the time. I met the author of the system, Joe Armstrong, in a conference about a month or so ago in the US. And we were talking a little bit about this. And I met somebody else a couple weeks ago at another conference. And he was telling me about how some network machines that they had would have like a backplane where if the entire switch failed, it would switch to the other one on the other side, right? And so physically, if anything failed, it would go and switch to the other one. And this thing was running for 20 years, and people were actually pulling components out of the other side because the first side never failed. This is a continuously running system which accommodates failure and is able to go and replenish itself when things go down. Now, this is not a style of programming you can use every place, but it's something which is kind of powerful to be able to go and handle, to say, look, if errors are normal, let's go and do the work that it takes to go and actually accommodate that. So yeah, fail fast is nice, but only if you have something which can catch you, something which will go and actually do something about the things that you care about. Now, what I find interesting is that these supervision trees we have in Erlang are an automated way of going and dealing with something that we can deal with ourselves, and quite often this happens. So say you're working at an e-commerce site like Amazon. If something goes wrong with your process, what do? You throw an exception, you can fail fast. Why can you do this? Because you have production support people that can handle the error 24 hours a day. Here's a problem, let's reboot things, let's go and do things like this. So we can have automated things in place to go and actually deal with errors as they occur, or we can have people in place to go and deal with things as they occur. Fail fast is actually nice for command line utilities because usually there's somebody there that can actually deal with the issue, and then you kind of move forward with things. So this supervision aspect is something that never really goes away. It's either automated or it's us, and it's something we have to kind of be aware of when we decide how to deal with errors. So yeah, the thing about Erlang is it's kind of like building giant networks of things, and it's kind of like it has some interesting parallels with biology also. That essentially you can look at processes as dying off and then they get replaced. It's just like biological systems where you have like an old tree dies and then you can have new buds that come up over time. So Erlang is a language which kind of like takes this insight of biology that essentially things don't have to be permanent. They can be temporal, they can be like transient, and still have a robust overall system. So we have a bunch of different avenues for things. As I mentioned a little bit earlier, one of the things we can do is we can finesse away errors. We can look at errors and say, how do we make this error go away? For the ones that we can't, we can look at things and say, look, how do we basically carry on processing in the presence of errors? There are many strategies we can use in the context of these things. So yeah, this kind of bulletproofing is important when there is no supervision. I want to tell you something else about this Erlang programming language, though, too. How many people have heard this thing recently that, dynamic typing is a problem? Have you ever heard this? Yeah, and in fact, there's a big push in the industry now to go and say, let's go ahead and make things as statically typed as we can. Let's go ahead and make things that basically allow us to prove that there are no errors in our software. That's great, but actually there are systems running in Erlang, I point out to this here, that can run for years, even though there are errors occurring because they took into account the possibility of errors. And guess what? Erlang is a dynamically typed language, okay? So there is no one solution for these things. You can be very strict in critical parts of your system, prove that errors can't occur, or you can consider errors normal and then go and proceed based upon that. Two different strategies. You have to pick which one you want. Okay? So it's not all about strictness. So yeah, I think what I want to kind of end off with, though, is a couple of thoughts. That essentially when you want to make design better, you have to consider all the cases. The sunny day case of like, here's the happy path through our program. Nice to go and get started with things. But look at things that can go wrong and go and ask yourself, can we avoid this? Can we either make that error go away by changing our requirements or going and doing work to actually deal with the thing that occurs early on so we don't have to make our code messy? And I think this is pretty powerful. It applies not only at the programming level, but also at the user interface when we start looking at things that might go and give people errors. Think about how to work with the user's intention. And yeah, essentially just challenge errors. And I think the overall thing with this is, that when we can increase the number of conditions our code can run under, it can run unconditionally. And I think this is much nicer. It's nicer for the user when we can just basically do the things the user wants, and that's great. It's also nicer for us because I don't know about you all, but I get really, really tired of looking at error handling code. Some of the craziest code on the planet. You have all these crazy things that can happen in the context of your code, all these if conditions all over the place, exceptions all over the place. I want code to be cleaner. It's easier for us, it's better for the system, it's better for the user. What else should we do, right? So anyway, thank you very much, okay?
So you said that you recommended using the null object as, well, basically an item with the message item not found and the zero value. So this is a recommendation to use something like this in that case when the item you want to display to the user was not found. But what you're doing here is basically you're encoding the error as a string. You're just putting some meaning on that string. It's still tunneling. It's just that the tunnel ends in the lap of the user.
Yeah. So this is the thing. It is kind of like a pun in a way to say this is normally the name of an item, but now we're putting an error message there. And so that may be good, it may be bad. I'm not recommending null object. I'm basically saying that's one option you have in the context of things. Some null objects actually work out perfectly fine, like returning an empty list when you expect a list of items, for instance. That's a null object also. So the thing with null object is it can be good, it can be problematic. What it really comes down to is whether anybody that receives the null object has to be aware that it's a null object. If it doesn't, then it can actually be okay. But yeah, I agree, there are complications with it sometimes.
So that code with the item not found you might find some developer who actually checks for the string item not found.
And at that point, then this is a place where this is not something you would actually go and need. Okay, so there are better examples of null object, I just didn't give them in presentation. So, yeah.
Thank you, and we have one more question over here.
Do you think that the fact that we have to think to a lot of error scenarios isn't kind of over-engineering because we are not able as a human to think to all of the cases?
Well, okay, that's true, but we are able to think about the cases where we have to do something in the code because of errors. I think that's really the symptom. If you are tempted to, if you have to check for an error in your code, then you should ask yourself, why do I have to check this? Can I design in such a way where I don't have to check or where this can't occur? Okay? So this is the rough part, is that quite often what we do is we code the happy path and we have then checks all through our code for things that can go wrong. Each of those checks is something we should think about. So we're already thinking about these things and we're thinking about them and putting checks in place. So it's about going and saying, let's question those when they occur. Can we have a simpler design where we don't need those? So.
Thank you again, Michael Feathers.